Okay, welcome back. So we have seen this. We have calculated the vertical load on the pulley A and we got that value as 3308.6 Newton and the horizontal force on the pulley B as 4964.13 Newton. Now we can represent all this on a diagram. So for that, the first space diagram we have constructed here. So let us draw this forces. For that, I can draw a line starting from this point C like this, and similarly a line starting from this point D, and another reference line, and I can drop these points B and A. So I can locate this point C, this is A, and this is B, and this is D. The first value we have to plot it is the torque. So we got this value for torque that can be represented here. So here I can take this value 357.42, that is the torque we are getting, that is 357.42 Newton meter, and I can draw a line like this to represent this is a torque, and I can write here it is a torque diagram. And similarly another line again here, and I can mark this point C, A, B and D. Here we have the vertical force acting on the point A, and we are getting that as TA1 plus TA2 is equal to 3308.6. So I have a vertical force acting in this direction. So I'll show that vertical force here. So we have a magnitude of 3308.6 Newton here. But at this point B, we don't have any vertical force. That magnitude is equal to 0. So if a vertical force is acting at this point A, that means at the support there should be an upward reaction. So I can represent that upward reaction at these 2 points C and D, then only the shaft will be in equilibrium. And I can write this as the reaction C V. That means it is a vertical reaction at the point C, that is RCV. And here it is a vertical reaction at the point D, so I can represent that as RDV. So this is a vertical load diagram. This is a vertical load diagram. And similarly we can draw another line like this. There also we can show this points C, D, B and C, A, B and D. But here we don't have a horizontal force here. But at this point B, we have a horizontal force that we can represent here. The horizontal force magnitude we are having it as 4964.13. That is the total horizontal force acting on the pulley B, that is TB1 plus TB2. So that means here we have to have a horizontal reaction. So I can represent the horizontal reaction at this point B as DH, that is RDH, and here it is RCV, the vertical RCH, that is a horizontal reaction acting at the point C. So this is our horizontal load diagram. So we have a torque diagram, we have a vertical load diagram, we have a horizontal load diagram. So in the vertical load diagram, we are having only vertical forces and vertical reaction at the support. In the horizontal load diagram, we have only the horizontal force and the horizontal reactions acting at the support. We know that because of this vertical load there will be a bending moment, so we have to find this bending moment because of this, which is produced by this vertical load, and we have to find out this bending moment produced by the horizontal force separately. That means we have to again construct two more graphs. That is, we can draw the vertical BM diagram, that is a bending moment diagram, and we can have a horizontal bending moment diagram, and finally we can have a resultant bending moment diagram. So all these points we can drop it here, and we can locate this point A, B. Similarly here, all these points we can locate, and we have to find out the maximum. This is a point A. So we have to find out the maximum bending moment produced due to this horizontal and vertical bending moment. So this is a diagram we have to complete. So I have a neat figure of this. So I'll show that. So we have to draw a figure like this. In this we have the space diagram, which represents the shaft, the pulleys and the side view. And then we have drawn this torque diagram, and we have marked this torque value, that is 357.42. And then we have this vertical load diagram where the reactions at the point C and at this point D, that is RCV and RCV, vertical reactions, and the vertical load, that is 3308.6, it is shown. And similarly we have this horizontal load diagram, that is RDH and RCH, that is the horizontal reactions acting at the point C and D, and we have the horizontal force. Now we have to individually find out the bending moment produced by this vertical load and horizontal load, and finally we have to find out the resultant bending moment, that is a resultant bending moment as shown in this figure. So let us do this calculation. So I'll take a separate sheet. We have to take a new page, and you have to do the calculation on a different page. So first let us calculate this vertical bending moment. So I have taken that small portion which represents this vertical reaction at the point C and at the point D, and the distance between this point A and C, as we know, it is 300 millimeters, and the distance between B and D, that is the 200 millimeters. And in this case we have only vertical load 3308.6 Newton. So let us find the reactions first. So for that we know this equation, that is sum of the upward force RCV plus RDV. These are the upward forces acting. That should be equal to the sum of the downward force. We are having this downward force as 3308 Newton, 0.6 Newton. So this is equation number. I'll put it as, in the previous slide we have seen the last equation, it is 4. So I'll write this equation as 5. This equation, it is 5. Now we have to find out this force CV and RDV. So let us take this moment with respect to the point C. So that is taking moments about the point C. We have two forces acting with respect to this point C. That is, one is the upward force reaction RDV. The second one, it is a downward force 3308. So the moment produced by this vertical force is equal to r dv into the distance between this point and this point. So we know the total distance between these 2 points, that is given as 1 meter. So I can write this as, when I take this moment with respect to d, I can write it as r dv into 1 meter, that is 1000 millimeter. The moment produced by this upward force, that is the sum of the clockwise moment, is equal to sum of the anti-clockwise moment. So we have this one, it is acting in the downward direction. So the moment produced by this is equal to 3308.6 into 300 millimeters. So we have 3308.6 into 300 millimeters. Now we can calculate this value RdV. We are getting this value RdV as 992.58 Newton. That is a vertical reaction acting at the point D. When we substitute this value in this equation number 5, we can find out this value RCV, the vertical reaction at the point C, that is equal to 3308.6 minus 992.58. So this answer, we are getting it as 2316.2 Newton. So we have calculated the vertical reaction at the point C and D. Now let us find the bending moment at these points, point C, A and D. So what is the vertical bending moment at the point C and D? We know that it is 0. So the vertical bending moment, I'll write it as mcv equal to mdv, that is equal to 0. The bending moment at the point C and D is equal to 0. Now we have to find out the bending moment at the point B, that is bending moment at the point B because of the vertical loading, that is MBV. So that will be equal to, we can take the moment from this direction towards this point, or we can take the moment from this direction towards the point. So if I take it from this direction, we will be having the reaction RCV, and also we will be having this downward force. But if we take it from this right direction, we will be having only one force. So this will be easier. So I'll take it the moment from the right direction towards this point B. So I can write this equation as RdV into the distance is 200 millimeter. We know the value for Rd as 992.58 and the distance 200. So the moment value, we will be getting it as 198.516 Newton millimeter, or we can write it as 198.5 Newton meter. So this is a bending moment due to the vertical load. Now we can find out the bending moment at this point A, that is MAV. There also we can take it from the right side. If I take it from this side, I'll be having the reaction RdV and this distance. And if I take it from this direction, it is RCV into 300. So I'm going to take it from this direction. So the moment is equal to RCV into 300.